So let's talk about the laws of thermodynamics themselves now in constructor theoretic language. So the zeroth law of thermodynamics says that if two thermodynamic systems are in thermal equilibrium with each other, or with a third one rather, then they are also in thermal equilibrium with each other. So this was useful, for example, in defining the notion of temperature. So how is the constructor theoretic formulation of the zeroth law an improvement of the classical formulation, or how is it different, or how are its implications different?
Yes, so I think this is a really nice question, because you're touching on exactly the point of this reformulation. So the reformulation of the laws in constructor theory somehow changed the order of the laws, in the sense that, as you were saying, usually they are given this way, that there's a zeroth law. Well, some people even talk about a -1 law, about minus first law, which is a very interesting statement, that it's about the existence of some kind of equilibrium in the first place. But so forgetting about that for a second, the traditional way of talking about the laws is that there's the zeroth law, which is about temperature and thermodynamic equilibrium. Then there's the first law, which is the conservation of energy, already mentioning work and heat in a sense. And the second law is then about this irreversibility, as we said. And then finally, there's the third law, which is about the impossibility of reaching absolute zero. And it's got, there are all sorts of qualms about whether it's actually as strong, as general as the others. But in constructor theory, on the other hand, the zeroth and the third law are, in a sense, more derivative, and specifically the zeroth law isn't needed. And so the way in which I approach the problem of the constructor theory of thermodynamics is that I approached the first and the second law as the backbones. So that's, my work is basically on those two. And then the question of how to rephrase the zeroth and the third is an open question. So it would be actually interesting to study that. And I think some of my collaborators are now working on that. But it's less fundamental than, so those two laws are less fundamental than they are in the classical thermodynamics. As far as the zeroth law is concerned, the reason why in constructor theory is not needed is that, to provide foundations for the rest, is that in constructor theory, the idea of temperature isn't fundamental. So usually in classical thermodynamics, it's necessary to start with the idea of thermodynamic equilibrium, and therefore with the idea of temperature, in order for then to be able to talk about the first and the second law, which are usually defined to hold around equilibrium. This is as far as classical thermodynamics is concerned. Of course, there are very nice generalization of this in the context of non-equilibrium thermodynamics, but I'm now talking about really the traditional formulation. In constructor theory, on the other hand, because the laws are, these two laws are now formulated in terms of possible and impossible tasks that involve attributes of physical systems, we don't need to assume that there is a temperature in order to, say, talk about these two states A and B that I was mentioning earlier, that define, let's say, the task that is then used in order to define what a work medium is or what a heat medium is. And so, likewise, there's no need for talking about entropy. So entropy comes in much later, in a sense, as a parameter that orders different tasks in regard to how impossible they are. In the, it's like it's just a function, let's say, that quantifies the degree of reversibility of a certain task. But it's not a fundamental concept, unlike, for example, what happens in the second law. So the answer to your question, therefore, is that the zeroth law in the constructor theoretic approach is a derivative law, so it's no longer like the foundation of the laws of thermodynamics, as it is in the traditional approach. And the reason is that in constructor theory, we don't need to assume the concept of thermodynamic equilibrium in order to state the laws, the first and the second. And they hold these two laws the way we formulate them. They hold irrespective of whether we are at thermodynamic equilibrium or not. What I expect is that you can retrieve the zeroth law in certain regimes as, say, some kind of approximation of the consequences of the first and second law of thermodynamics as I formulate them in the constructor theory framework. And I think, as I said, this is work in progress. So it's a nice question that you asked, because it's kind of pointing ahead in terms of what is it that we will do in the future.
Let's talk about one of the more fundamental laws in that case of thermodynamics as formulated by you in constructor theoretic language. So let's talk about the first law of thermodynamics, which traditionally is kind of, I think you said this several minutes ago, it's a way of formulating the principle of conservation of energy. Another way of expressing the first law of thermodynamics, I think, is basically that all ways of doing work are interchangeable. So how is the constructor theoretic way of expressing the first law different from traditional formulations, and why is it an improvement upon it?
So there is a very interesting fact, which has to be, I mean, it's already something that you notice by looking into the standard formulations of the conservation of energy. And this fact is that there is one way of formulating the conservation of energy, which is really more or less scale independent. So this is the form I just mentioned earlier. So the form that I mentioned earlier is that it's not possible to generate energy out of no energy without any side effects on surroundings. So, I mean, this is a kind of obvious example, but let's say when you want to charge the battery of your smartphone, that can't happen spontaneously. You need a source of energy. So you need to plug in your iPhone somewhere and let it charge. And this depletes the energy, the source of energy that you are using. And so in a sense, whenever energy is being increased somewhere in the universe, it must decrease somewhere else. This law, formulated this way, does not mention heat and work. So that's the kind of law that I find more interesting, because it's not based on work and heat. It's not scale dependent, so it's universal, and it's not only valid for the semi-macroscopic systems. But then if you go in traditional thermodynamics, what you call the first law is this idea that the amount of work and heat that are being produced in a certain process have to be also kind of subject to this conservation of energy, and that work and heat together make up for the total energy change of a given system. Now, the problem with this first law formulated in this way is that it already refers to heat. It's kind of paradoxical in a sense. It already refers to heat, but no one has or explained what heat is. Usually heat is kind of defined as kind of in a very vague way as stuff that isn't work. And really the gap in the conceptual gap in the first law of thermodynamics formulated in this way in terms of work and heat is that heat on the one hand is introduced at this stage, but it's only later with the second law that we say why heat has to be at all present in the universe because of the kind of dissipation that is introduced by certain processes that the second law mandates. So in contrast, I think in constructor theory, we revert, so that we somehow talk about the first law in terms of the pure conservation of energy in the form that I said at the start. With two important differences, and I think this is very nice to point out. So the first difference is that, and this is a bit of a technicality, so I'll try to make it as comprehensible as possible. So the first, the conservation of energy in the form of the universe has, you know, the overall energy of the universe is constant, and therefore if a subsystem of the universe has its energy changed, then some other subsystem has to change the energy by an equal and opposite amount. Is not very helpful because it doesn't quite say whether the energy has to be bounded. So the idea is that there has to be, for example, a minimum energy, but there may or may not be a maximum energy. So you could, in principle, increase the energy of a system as much as you like. And in order to put bounds on an upper bound on the amount of energy that you can put on a system, you need to use other considerations that come from, let's say, outside thermodynamics. In constructor theory instead, when we say the task of changing the energy of a system is impossible, because we are referring to, because as I said, impossible means it cannot be brought about to arbitrarily high accuracy. That puts both an upper bound and a lower bound on energy. So energy is now bounded both from above and below. So it can, and the energy of the system is not just, I mean, doesn't just have a minimum, but it also has a maximum. So it cannot exceed, it can't be infinite in both directions. So it cannot be infinitely large or let's say infinitely negative. And I think this is important for various reasons, but specifically for a reason that's connected to the second point of difference in the first law of thermodynamics as formulated in constructor theory, which is that energy usually is defined in either the thermodynamics way through work and heat, which we said we don't like because it's scale dependent, or it's defined specifically in a certain dynamical framework. So for example, if you have Newtonian mechanics, you can define the total energy as a certain function of the position and velocity of the particles that constitute your system. And then if you have quantum mechanics, you can then define likewise the total energy operator in a certain way and so on. And then you can prove that these things have to be conserved under the specific dynamical laws. But by the way, sorry, in general relativity also, the concept of energy no longer makes sense in the sense that we define it classically. You have to define something called the stress energy tensor. And so therefore the idea of conservation of energy as classically conceived breaks down in GR, and one has to resort to a more general concept of conservation. In constructor theory, the concept of energy isn't defined through a specific dynamical law, but it's defined through the impossibility of certain tasks. And by doing this move, we don't have to root the second law, the first law in a specific dynamics. So the concept of energy is much more general, and it can embrace all of the concepts of energy that are definable within each dynamical laws that as I just mentioned now, but it can also embrace new concepts of energy that could be, proposed in a future theory of physics that we haven't yet formulated. So I think these are the two main differences, let's say, in the approach of the constructor theory to the first law. The first difference is we don't use already heat and work to define the first law, unlike traditional thermodynamics. So it's a scale independent formulation, only in terms of the fact that certain tasks are possible or impossible in a physical system. And the other one is that as a result of that, the energy is bounded both above and below. And the other one is that the energy is no longer identified with a specific function which can be defined within a certain dynamical framework, but it's a more general concept which kind of encompasses all the dynamical instances that we know of it, and hopefully will also underlie the ones that haven't yet been proposed.
And is there a connection between information and the first law of thermodynamics that constructor theory revealed?
Yes, so that's a nice point there, because the so once you assume once you formulate the first law in this way, then you can introduce the definition of work media, and you can explain, you can say what they are in terms of requiring certain tasks to be possible on this class of systems. And then something very curious happens without even bringing in the second law yet. So this is only really based on first law as formulating constructor theory, which broadly speaking is about the conservation of energy, and the definition of work media. Then you notice that work media, which are this generalization of mechanical means, of the concept of mechanical means in classical thermodynamics, must have a specific information theoretic property. So particularly, you can show that this work media must have a set of states that are distinguishable. So the fact that you can use a system in order to do work or to extract work from it implies, under these definitions that I just described, that the system can also be, can also be used as a storage of information. So it's states, it has to have a set of states which are its work-like states that are distinguishable in the same way that, say, the states of a bit are distinguishable and can therefore be used in order to carry information. So this is the way I described it is very informal, but this can be expressed rigorously in kind of the constructor theory language. And so it's basically says that work media are information media. So this is quite nice because it's it connects the realm of thermodynamics to the realm of information theory, not through the second law, which is the usual connection, but through the first law. And this is a very interesting fact, because usually, as I said, the connection with information theory occurs through the second law. But in this case, we can go directly via the first law. And so in a way, this tells you that whenever you have something that you can extract work from, you can also use it to somehow encode information, which is very cool. It's a very general and kind of also novel connection that comes out of this constructor theoretic approach.
And you mentioned the second law briefly and its connection to information, which had previously been thought of. Now, the second law of thermodynamics, traditionally speaking, states that the entropy of an isolated system never decreases over time in the long run, something like that. What is the constructor theoretic formulation of it? And why is this an improvement over the traditional formulation?
So as you said, I think the law as you formulated it now, it's basically the statistical mechanics law, and it kind of says that the entropy of a system either stays unchanged or increases. And this is, usually when one states this law, one has to specify that this is true. The entropy increase part is true probabilistically. So you can say it's overwhelmingly likely that the entropy of the system in question will increase. But of course, there are some trajectories and behaviors of this physical system in question where the entropy actually can decrease. And obviously this happens when you consider various interactions between microscopic systems and their counterparts in the context of a completely reversible dynamics. So in some sense, people who phrase the law in the way you said are happy to say that the best way to phrase it in, following the way you suggested is to just say the entropy of an isolated system never decreases. And then if you're considering a single molecule which is isolated, you will just expect the evolution to be unitary according to quantum theory. And that means that the entropy actually is unchanged, so it stays the same. And so in a sense, the law in that sense would be still true for single particles, but it would be trivial because it doesn't tell you more than, it doesn't prescribe any reversibility and doesn't tell you really more than what the dynamical laws already tell you. And so you could just scrap it and say, well, I'm gonna keep the dynamical laws and that's it. And in a sense, as I said, the camp of physicists who thinks that the second law is not fundamental are thinking a bit like that. So they say, well, ultimately I'm just using the dynamical laws, and it's only where it's a bit intractable to follow all the particles, I will use this second law and telling me what is the most likely output of the dynamics in this context, assuming certain specific interactions and so on. In constructor theory, on the other hand, we are very happy with the fact that entropy somehow, as I said, loses its central position. So entropy only comes in much later. We're very happy with the fact that the dynamics is time reversal symmetric, so we don't worry about that. But we still say that for certain tasks, there is an irreversibility, and this is in the form of the task it's possible in one direction, but it's impossible in its reverse direction. So the specific thing is that the specific formulation would be something like there are states A and B of a physical system with the property that the task of going from A to B with side effects on work media only is possible, but the task of going from B to A with side effects on work media only is impossible. And of course, we here possible and impossible don't mean allowed, as I said earlier. Here, the two key things are, one, work media are defined in the scale-independent exact way without using specific dynamical laws. And so they are more general than this idea of a mechanical means that was kind of the basis of the original axiomatic thermodynamics. And the other thing is that because the law is formulated in terms of possible and impossible tasks, even though it requires an irreversibility, which could be true for even just a single particle, a single qubit, going from state A to state B, so the law isn't in conflict with the reversibility of the dynamics of the qubit, because it's not about which trajectories the qubit can undergo when it's isolated, but it's about which tasks you can perform on the qubit when you allow the qubit to interact with the environment. And the only requirement is that the environment somewhat performs the task and then stays unchanged in its ability to cause it again for the task to be possible. And so with this trick, in a way, you can still have irreversibility and formulate it as a requirement, formulate the law, the second law, as a requirement on irreversibility being fundamental and exact. But at the same time, you can still say, well, I can have laws that are time reversal symmetric that describe macroscopic dynamics, and these two facts are not clashing with one another.
So to end, with a scale-independent exact theory of thermodynamics, or an exact expression of the laws of thermodynamics using constructor theory, what problems outside thermodynamics do you expect these laws to help solve in the future, or do you hope that they might solve in the future?
So I think this is really an open field, and I should say that there have been already lots of efforts from the community of statistical mechanics and of quantum thermodynamics of trying to generalize the laws of thermodynamics in a way that they include quantum systems, microscopic quantum systems as well. And specifically, quantum thermodynamics has improved greatly on the statistical mechanics of non-equilibrium, and trying also to relax all sorts of assumptions in terms of the number of systems involved in the physical processes for the second law to hold. And there are various generalizations in the context of quantum thermodynamics of the second law. But what's missing there, in my view, is that, which I think constructor theory is trying to provide, is that in that case, we are really grounding the thermodynamics reasoning within the dynamical laws of quantum theory. And so, in a sense, this is like pushing ahead the statistical mechanics program by augmenting it and relaxing some of its assumption to include fully the quantum dynamics. In the case of constructor theory, on the other hand, we are trying to keep the same generality as the original traditional thermodynamics laws, where we really didn't have to know which particular laws, which particular dynamics or laws of motion the elementary constituents of the matter obey in order to say that, say, the second law is a good guideline for designing a heat engine. And we are trying to do that by so not committing to specific dynamics, but also by keeping the law as scale independent as possible. And so in terms of applications, I think the stuff that I'm doing will have the same range of applications as, say, some of these quantum thermodynamics proposals, in the sense that you could try to apply these laws to microscopic systems which operate, let's say, in nanoscale cycles, where you're trying to mimic the behavior of a heat engine, but you are trying to do so at a very, very small scale. So, for example, within a quantum computer. But also, the applications should be more robust than that, because they shouldn't only apply to the specific case of quantum theory, so of quantum systems, but they should analyze the physics of objects where quantum theory may fail. And chiefly, this is the case where quantum systems interact, for example, with gravity, where we don't know which particular form of quantum gravity we should use in order to describe what's going on there. So quantum theory is a bit out of the way in that context, unless we specify a specific model, but then we don't know if we are committing a mistake. And so in that case, it's very important to have these general principles that are not assuming a specific dynamics to be true. And the second law in constructor theory has this feature, and the same for the first law. And then, of course, there are all sorts of applications in the context of the foundations of information theory, because if, as I said, there is this promising connection between thermodynamics and information theory through the first law and the concept of work media, That is very promising because it suggests that this bit of work that I just described in constructor theory, the constructor theory of thermodynamics, could be the first step of what von Neumann called the theory of the universal constructor. So the universal constructor is this machine that generalizes the universal quantum computer from a machine that can perform all computations that are physically allowed to a machine that can perform all tasks that are possible. So you can think of it as a bit of a like a super powerful 3D printer, the most powerful 3D printer that can exist in the universe. And this object, the universal constructor, when programmed with the right knowledge, can construct any object that is physically permitted. And of course, to describe it, it's not possible just to use the laws of information theory that we know, not even the laws of quantum information theory, because it's not just processing information, it's doing other things. So it certainly will be ruled by the laws of thermodynamics. And so having a law of the first and second law of thermodynamics formulated in this scale independent way provides, let's say, a first layer of principles that this constructor, the universal constructor, should obey. And based on that, I think hopefully it will be possible to build more and more layers of this theory until we will kind of have a nice theory of the universal constructor, which will somehow have the same far-reaching consequences as hopefully the theory of the universal computer as Turing proposed it, which then powered, the IT technologies that we are all using now, and kind of they are saving us from the pandemic. And I think the hope is really that this work stretches, brings together the foundations of physics, and specifically quantum physics, if you like, with the foundations of information theory and the foundations of thermodynamics, and provide some conceptual basis to build something much broader.
Sounds very ambitious. Looking forward to seeing how this all unfolds and works out throughout the years. So Chiara, thank you very much for your time.
Yeah, thank you very much for the interview. I really enjoyed it. Thank you.
Thanks. Take care.